So in this chapter, we are going to look at a different part of multivariable calculus, which is the differentiability, the differentials, and the local linear approximation. So at the end of this lesson, you should be able to identify a function to be a differentiable function, or for you to state whether a function is differentiable at a given point, and also you should be able to write a function in a differential form. And when a function is given to you, we should be able to find the linear approximation of function. So let's get with the differentiability. So now I'm going to go straight to what you must understand by a function being differentiable. So per definition, from here, we are going to read together, and I will explain that. They said a function of two variables is said to be differentiable at x naught and y naught, which means that is the given point, provided that the partial derivative of the function with respect to x, and then you insert the point given to you, x naught and y naught, and the partial derivative of the function with respect to y, you insert the values given to you, that's the point x naught and y naught, both exist. So then when you take them and you follow them and you will insert the value, you should get a value, which means that they should exist. So per this, the limit as change in x and change in y approaches to 0, the change in the function minus the partial derivative of the function with respect to x, you've inserted it, times the change in x minus the partial derivative of the function with respect to y, you've inserted the x naught and y naught, times the change in y, all over the square root of the change in x squared plus change in y squared should be equal to 0. So this is the rule that it must be. So when a point is given to you and they're asking to check whether it is differentiable, at the end you should get 0. We are going to take an example. So let's take this example for us to understand. So using definition to prove, so we are going to prove that this is differentiable at 0, 0. So first we need to find the increment. The increment is that the change in f is equal to, that's the function x naught plus change in x, comma y naught plus change in y, minus the function itself. Then you're going to put the point given to you into the function itself. And when you do that, you're going to get this as an answer, right? Yes. Then you go to the f of x, because the formula is this. So we've gotten the change in f, and we are going to solve for this one. That one, when you do this, this is the function given to us. You know that we've done this, the partial derivative, you're going to get 2x, because this is going to change to 0. And with the y, you're going to get 2y. Then you're going to put the values inside. You know, when you put 0 inside, you're going to get 0. And then it means that when you put 0, with this is 0, with this is 0, right? That means you're going to get only the change in f all over the square root of change in x squared plus change in y squared. And you're going to take the limit as change in x and change in y approaches 0. You're going to expand this. And I think when you expand, it's going to cancel out. And at the end, you're going to get what? 0. Which means is that, this means, you getting 0 means that the function is differentiable at that given point, because it satisfies the equation, this one. So whenever they give you a function and a point and ask you to determine whether that function is differentiable at that point, you need to use this principle to identify it. One, they must exist, and also when you take their limit, they should, using this formula, you should get 0. The same thing applies to the 3 variables. So let's go to the 3 variables. With the 3 variables too, you're going to get, you see, they'll give you 3 points, which is x naught, y naught, z naught. So the same thing application. So you are going to take change in f, then you are going to take the partial derivative of the function with respect to x, insert the value, then multiply it by the change in x, the same thing, and you are good to go. The change in x, let me explain. The change in x is just x minus x naught. Change in y, y minus y naught, is like finding the changes, like the slope. In this case, you are finding it along only x-axis. That will be x minus x naught, right? Yes, so that's all about the differential. Move on to the next one, which is the when we talk about, we've done all this in the video. Yeah, that one, previous one. So let's go into differentiability and continuity. So if a function is differentiable at a point, then it's continuous at that point. So they can ask you is a function differentiable? Then if it's differentiable automatically, per the definition given here, it is also continuous at that point, right? With the differentials, what you must do is just a simple thing. I think we've done this in our previous video, which is this formula, the z. In this case, you are just going to take the partial derivative of x, the partial derivative of the function with respect to their corresponding variables, and then you insert the values given to you in it, right? As you can see here. So this was the proving, and after proving they had this. So the z is what? The partial derivative of the function with respect to x, and then the the x naught and the z naught dx, because you are doing with respect to what? X. And then we did this in our previous video. So with this case, you're going to insert the value, right? The same thing applies to when they give you the three sets. And in the three sets, we are going to use this one. This is how we call this. So when they give you a function and say change it to differentials, or you need to consider this one as differentials. Is it also called the total differentials? I said it in that video. You just need to find the partial derivative of the function with respect to their corresponding variables. Then you are going to input the point given to you. So when you're doing with respect to x, after inputting it, you're just going to add the x, y, the y, and z, the z. Yes. So let's go to the local linear approximation. So in local linear approximation, let's go to the slide. Equivalence, we can write the approximation as the change in z is approximately equal to what? The dz. If a function of f is differentiable at a point, then it can be very closely approximated by a linear function near that point. So in this case, we are proving to find a formula in which we can use to find the linear approximation, right? So now what you must know is that the function z naught, you know that this is change in f, the one that we did change in f, right? So z x naught plus change in x comma y naught plus change in y. And I told you that the change in y, this one change in x and change in y is x minus x naught, y minus y naught. So at the end, you know that z is x is equal to x naught plus what? Change in x. And y is equal to what? Y naught plus change in y. So at the end, when you do the approximation, this is the formula you're going to get. So with the linear approximation, this is what you're going to get. So they're going to give you a function, and then they're going to give you the point at which the function is differentiable, right? Then you are supposed to find the linear approximation. Simple, you're going to use this formula to find the linear approximation. So with the linear approximation, you're going to take the function itself, then you put the point given to you in the function, then plus you're going to differentiate the partially differentiate the function with respect to x, then you put the values inside, then time the change in x, which is x minus x naught. Are you getting it? From here, you can make change in x the subject, you are going to get x minus x naught, then plus you are going to differentiate the function with respect to what? Y, then you input the values, the point given to you inside the y, then you're going to multiply it by the what? The y minus y naught. So in this case, we're going to take an example for us to understand very well. Example, with this example, now the question is asking us to compute the error in approximation, right? So this represents the linear approximation, donate the local linear approximation from the function x and y, which is equal to the square root of x squared plus y squared at the point 3 and 4. So do you know what? This point 3 and 4 is from this approximation. So this point has been approximated to 3 and this point has been approximated to 4. So in this case, they are asking us to find the error in this approximation, right? Yes. So now what you must first do is that for you to know the error in approximation, you take the function, then you put this represent the x value, right? This is the x value, and this is what? This is x value, and this represent the y value. But in this case, with this point, this is x naught and y naught. So then you want to find the error in the approximation, that when they've approximated this to 3 and approximated this to 4, what will be the error? So first, you're going to take it and put inside the function given to you. And when you do that, this you're going to get 5.000819, right? So then we are going to use the linear approximation to find the linear approximation, the approximation after approximation. Then we'll take the difference between this and the linear approximation to find the error. So first, let's go with the linear approximation per the formula we proved, right? First, you need to get the partial derivative of the function with respect to x, and in this case they gave us square root of what? X squared plus y squared. And this, you can change this to what? Bracket open, this will be s squared then plus what? You get y squared, right? And all exponent half because it's the square root. So when you are doing partial derivative with respect to x, it means that you're going to bring this half in front, which will give you 1 over 2. Then you partially differentiate the x, I get in it, which will give you 2x. Then you subtract 1 from the function, which will give you negative half. So at the end, you're going to get the 2x will cancel the 1 over 2. So 1 over the 2 will cancel the 2, giving you x. And since this is exponent negative half, you're going to bring it down and bring the square root. That's why they had this. And the same thing applies to these two. You get the same value. Then when you are done with that, you are going to insert the x naught and the y naught into the function, because when we did the when you prove it, x naught and what? Z y naught. So when you do that correctly with the f of x, you're going to get 3 over 5. When you do that with the f of y, you're going to get 4 over 5. Then you're going to insert it into the what? The linear approximation, the local linear approximation formula at the point x naught and y naught. Note that x naught and y naught has been approximated from x and y. So here, you're going to put a value inside, finding the function and inserting it inside. Because from the formula, you need to find the function and just put x naught and y naught inside. So when they did that, they had 5. And then this will be f of x times change in x. In this case, it will be x minus x naught. And in this case, they gave you x naught and plus f of y change in y, which is y minus y naught. You can also get it in 3 variables. You should follow the same procedure. So then what do? We note that from the question, we know that this x represents the value which we approximated. That is 3.04, and the f of y is the value in which you approximated with the y value, that which is what? 3.98. So we are going to insert it inside, and when you insert it inside, you know when you take the difference, you're going to get 0.04, and here you're going to get negative 0.02. So when you do that correctly and you get the linear approximation, the local linear approximation will give you what? 5.008. But when you take the value in which we approximated and we place it directly into the function given to us, we're going to get 5.00819. So then we want to find the error. In this case, we are just going to subtract the local linear approximation from the function, that is the value which we approximated, that we inserted into the function given to us. And at the end, as they've done here, you're going to get that the error here is going to give you 0.00019, which is less than 1 over 200 of the distance, right? So you can also find for the distance. You know that the distance is what? Square root of change in length. That's change in x squared plus change in y squared. And in this case, change in y is x minus x naught. Change in x is x minus x naught, sorry. And change in y is what? Y minus y naught. And you're going to get 0. This will be the distance, right? That's why they say that this is the value you had, the error in the approximation that you had is less than 1 over 200 of the distance. So this is what you should know about the local approximation, and it's very simple to do it. So thank